Saxon Algebra 1, welcome to lesson 84. We have two topics that have precious little to do with each other. For the first feature, we're going to multiply radicals. It's easy and fun. Are you ready? Here's the basic rule. If you're multiplying pigs and houses, you can just put them in together. Okay? And conversely, if you've got two pigs being multiplied in the same house and you want to break them out, you can. Okay? So this rule works both ways, but it's pretty straightforward. So let's look at an example. Now, you're going to have to live with my metaphors here. You know, I think of these numbers inside the radical signs as pigs. They're the three little pigs that are in their houses, right? And the wolves are on the outside. They are huffing and puffing and trying to get at those pigs, right? Okay, so when we multiply radicals, we multiply wolf by wolf, and we multiply pig by pig. We don't combine them. So I dare to put that in a puffy cloud of knowledge. So to do this one, we would do wolf times wolf, 12, pig times pig, 6. That's our final answer. Is this not a dream come true, how easy it is? Let's see if it gets any harder. Next one, ready? Wolf times wolf, pig times pig. 24 is the wolves. Pigs, oh wait, I did this wrong, there. This becomes 18, okay? Now, that's correct, but we look at this and go, whoa, 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 we can break this down. 18 can be broken down into 3 times 3, which is 9, times 2. And remember, for every pair of pigs we have on the outside, we can bring it, on the inside rather, we can bring it out as a single pig. So this will multiply to what? This will be 72, and then we'll just be left with 2 on the inside. So we can simplify these by bringing out pairs of pigs to join the wolf, right? Because here's the thing, a single pig wants to hide in the house, but if there's a pair of pigs, they can go out and taunt him and stand up to him. So that's fine. I know, just work with me. Page. Example 84.3. Ready? This is distribution style math, right? Multiplication. We do it just like any other distribution, right? First and second. And we do the same thing, wolf times wolf, pig times pig. Wolf times wolf is 20, square root of 6, plus, okay, let's think this one through. 4 times 6 is 24, but 3 times 3, well, that's going to put a pair of pigs together, right? We can split those out. So we can take the 3, bring it out, multiply by the 24, and be done. So this will be 20 times the square root of 6 plus, that is 72. And that is our final answer. And that is a perfectly fine way to format the answer. All right? And then our last one of this part A is another distribution. Okay, we multiply wolves and wolves, pigs and pigs. Wolf and wolf is 12, but look, so I'm going to bring a single pig out. That's going to give me 12 times 2, which is 24. Plus, right, do you see how I did that? These two 2's on the inside came out to be a single pig, a single 2 on the outside. And now we have to do this. This will be 20 square root of 2. Final answer. Okay? 2 pigs on the inside equals 1 pig, a super pig, you might say, on the outside. All right? And we add him to the wolves. No, we don't add, we multiply. Okay, another important piece of information. All right, that's part A of lesson 84. Part B is about functions. Functions, most students consider functions either super hard or super easy, depending on how it's been presented to them in the past. I'm here to tell you that functions are super easy. They're just a new way of thinking about what you already know. All right, let's say that I told you that we had an equation where y equaled x squared plus 5. And I asked you to calculate some points based on that equation. And I said, here's going to be some x values. I want you to calculate the y values. And I gave you these x values. Right? And I told you to calculate the y's, right? So you would say, okay, 2 squared plus 5, that's 4 plus 5, that's 9. 4 squared plus 5, that's 16, plus 5 is 21. 7 squared plus 5, okay, that's 49, so that must be 54. Okay? That you would probably, I hope, you would say, that's pretty straightforward, that's easy. Now what we're going to say is this is all that functions are. What we do is we draw a slightly different kind of picture, and we focus on the connection between these points. So, a function, a mapping of a function could look like this. There's different ways to portray this. This is one way of mapping this function, because we say that for every input, every x value, we calculated a specific corresponding value. And we might even write over this x squared plus 5. And that is the function. It's the fancy word we use for that. And we might call this the domain, which another way of thinking of this are the inputs. And these we often call the range, which are the outputs. Okay? I gave you the domain, you calculated the range. Okay, technically I calculated the range, but you could have if you would have been sitting here, right? So, a function is a mapping of inputs and outputs in which every x, every number in our domain, has one and only one y value attached to it. See how ours worked here? That's perfect. That's an indication of a proper function. Let's look at, I don't want to use the book because it's hard to see. Let's go into our problems. The question says, does this diagram designate a function? And this is the way it looks. I'm on the top of page 348. If you're with me, you don't need to have the book though. 4, 5, 6, 7, 2, 14. And there's arrows connecting, and then it says domain and range. I'm not going to take the time to write that out. Is that a function? Every x has one and only one y. Yes, this is a function. Okay. How about the next one, 84.6? My function ovals are kind of wonky, but it's okay. YAM. What the heck? This has letters. Guess what? We don't care. That's not the issue. The issue is, does everything on this side have one and only one partner here? This is domain. This is range. We can also think of this as X and Y, if that helps us. Every X has one and only one Y. So let's look at how the arrows go. Boom. Boom. Tracy's up. Okay, this one's a problem because look at M. M connects to X and 5. No bueno. That does not work for a function. No, this is not a function because M goes to X sometimes and 5 other times. That's a deal breaker. That means it can still be something interesting, but it's not a function. 84.7. Does this designate a function? Domain, range, A, 4, and 7. Okay. Look at how the arrows work on this one. Now, the natural reaction is to get a little upset about this whole thing where A and 4 are both pointing to 5. But remember our rule. Every X has one and only one Y. It's okay if they share a Y, but A only leads to 5 and 4 only leads to 5. So yes, this is a proper function. Okay. This one looks weird. This is the domain, this is the range. This says real numbers. And then there's an arrow that goes like this, and it says y equals x plus 2. Okay, so what this diagram is saying, we can use any of the real numbers and plug them into this function, this equation, and we'll get out whatever we get out. The members of the range are not specified, but we can use this information to fill this in. So we would say, yes, this is a proper function because we're only going to get one value over here for any number we choose over here. So that is a perfectly fine function. There's more of these. We go up to 12 in this lesson. Yikes. Okay, but they're easy, so it's fine. Now, what we're going to do, remember back here how we set up this little table, right? And we calculated these values. I gave you the values for x and you calculated for y. We could write these as pairs of points, couldn't we? See, I'm just using the x and the y and I'm writing them as an ordered pair. And if we were trying to apply our rule, every x has one and only one y, we could look at points like this and test whether or not it's a function by looking to see if there are any duplicates in the list of x's. We would look just at the x's, and then if there were any duplicates, we would look to make sure that they were both partnered with the same y value. If the point was listed more than once, but it had the same y value for that x, we would be fine. So let's look at 84.9. Point A, because we're using this formatting here. And it gives us 3 pairs of points, just like we were just looking at. And look at the drama. So we look just at the x's, and we look for any repeats. Aha! We have 2 pairs of points that both lead with a 4. This one is attached to a 6, and this one was with a 5. So this is no, not a function. Right? Because the same x value is partnered with different y's. B. 4, 8, 15, 6, 11, 7. Okay? So the first step is to look through and see if there are any matching x's. No, all the x's are different. So as far as we can tell, yes, this is a function. Looks good. Okay. Example 84.10. Oh, there's 4 of these. That's so much to write out. I don't know if you can read this, but again, what I'm going to do is I'm going to look through the list at the x's. 1, 2, 3, 4. Okay, there's no repeats, so that's probably, that looks like a function based on what we see. B, 1, 2, 1, 4. Okay, so there's 2 that have 1 for the x value. The first one's partnered with a y of 2. The other one's partnered with a y of 3, so B is not a function. A is a function. Or does it say B is not? That B is not a function. C, 4, 2, 4, 3. Okay, it repeats the 4s. So then we look at the y's. This is 4, 3, and that's 4, 3. Okay, so both of the 4s are partnered with the same y value. So C is a function, yay. And then D, 1, 4, minus 1, 3. Okay, every single one of those x's is different. So as far as we can tell, D is a function. Okay, we're happy. 8411, does this diagram designate a function? Okay, 7 is cool, 7 goes to 11, but 6 is going sometimes to 4 and sometimes to 8. No, that's a deal breaker, so we say no. Okay, how about this one? 6 goes to 4, that's cool, 7 goes to 11, that's cool. 5 has nothing, oh my god, not a function, 4, 5 is denied. Okay? It says, does it designate a function or a relation? And this explains that for a correspondence to be called a relation, there must be one or more images for each element of the domain. So a relation is less picky, but everything has to have a partner, and poor 5 is a freak. So this is neither a relation or a function. This one is a relation because every x has a partner. It doesn't have a legitimate partner to be called a function, but it does have a partner, so we can call it a relation. Where did John tell us about relations? Here it is. A relation is defined as a pairing that matches each element of the domain with one or more images in the range, okay? So, like this one we said was not a function, it's a relation. All right, so a relation is looser than a function. All right, finally we did all of the problems so you can see for your practice. We get some wolves and pigs. Don't they seem like a breath of fresh air compared to all this picture business? And we want to know which ones designate functions. This is cool, that's not cool. Here are some with the pairs, and then we're into the regular homework. Lesson 84, enjoy it.